A while back, I hopped on Minecraft, set up a base, and decided to dig out a 10 by 10 square area to plant sugarcane. However, it got me wondering, what is the best way to plant sugarcane? See, one way is to alternate between rows of sand and water. Or, a better way is to do 2 rows of sand instead. Of all these options, how can we find the best one? Let's first rephrase our objective a bit more formally. Given an n by n plot, how can we place sugarcane to maximize the amount produced? Turns out, problems like this can be modeled and solved using a field of math called optimization. When formulating an optimization problem, there are 3 main features. 1. The variables which describe our problem. 2. The objective function, which is the criteria for what we want to minimize or maximize. And 3. The constraints on the variables being optimized. In our case, every block has to make a discrete choice between water or sugarcane. Since we can't have a mix of both, this means our problem is modeled by an integer program. An integer program is a type of optimization problem that, in general, can be written as the maximization of some linear function f, subject to m linear constraints, with all or some components of x required to be integers. With this in mind, let's model a farm. We'll first define the variables. As we want to know whether each square is a sugarcane or water block, let x sub I, j correspond to the block on the ith row and jth column. We'll give it a value of 1 if it's a sugarcane block, and 0 if it's water. And such a variable with just 2 choices is known as a binary variable. Now we model our objective, which is maximizing the amount of sugarcane we can plant. Since each square is represented by either 0 or 1, simply adding up all the squares gives us the total number of sugarcane planted. Lastly, we move on to constraints. In Minecraft, sugarcane must be placed cardinally adjacent to water. In other words, the water source cannot be placed diagonal to the sugarcane. To represent this, we'll introduce a function n, which takes a position I, j, and returns a set of valid neighboring positions. We'll use this to check whether we have water around a sugarcane plant. But our current definition of n has an issue. On a corner, for example, position 1, 1, n returns indices which are invalid. To deal with this, let's have a look at the following. Consider any valid position PQ on the grid. We can measure how far it is from ij by taking the absolute difference in the row coordinates plus the absolute difference in their column coordinates. If we plot this value around ij, we notice that the 4 squares directly adjacent to ij are exactly the squares with distance of 1. Now, we can redefine nij to contain every valid position pq whose distance from ij is exactly 1. Checking n, 1, 1 again, we see that n returns the right values. We can now use n to model the relationship between sugarcane and water. Since water is represented by 0, the expression 1 minus x sub pq equals 1 whenever a neighboring block is water. So, by summing all 1 minus x sub pq over every block in n, I, j, we can count how many water blocks are next to I, j. If I, j is a 1, then we need at least 1 water block nearby. Otherwise, we don't need a constraint at all. This can be represented by the entire summation being greater than x sub I, j. Put together, this is our integer program. And to solve this, we'll use Google's CP-SAT solver, which is designed for constraint optimization problems involving integer and Boolean variables. Now we can get started. Let's first import our required libraries, then define a sugarcane solver class, which contains our plot size n, an OR tools model, and the solver as well. We'll also define our variables x to be in a dictionary. Then we're going to set these variables all to booleans, since they're binary variables. Then we'll define our objective function f, which takes the sum of every single x within our grid. We'll set this objective using the setObjective function and setting it as the maximize in the model. Then we'll define n of ij, which returns all positions that are immediately adjacent to ij. With that, we can model every constraint for each square. Finally, we're going to solve it. And here's some code to quickly visualize what our solution looks like. So we'll first initialize the sugarcane solver for size 10. We'll set the variables, set the constraint, and set the objective to be our function f. Then we'll solve it, and then plot it out. And just like that, this is what the optimal solution for a 10 by 10 grid looks like. Here are also some other interesting ones I found. I then tested other farm sizes and plotted the percent coverage against n. For small values of n, the solver can prove optimality, but beyond about n equals 14, proving that a solution is optimal becomes computationally expensive. So for larger n, the plotted values are the best feasible solutions found within a fixed time limit. The coverage seems to approach about 80% as n gets large. Turns out there's actually a reason for this. Let's have a look. In the 13 by 13 layout, a lot of the grid is tiled from a flower pattern. There's one block of water in the center with 4 sugarcane around it. This means locally, about 80% coverage is achieved. But the full grid is not a perfect tiling of these flowers, especially near the edges, where some petals get clipped. But as n gets larger, the edge effects become less important compared to the area of the whole grid. The solver's layouts look like an attempt to cram as many flower patterns as possible, which is why coverage tends towards 80%. And that concludes our exploration into planting sugarcane. I hope you enjoyed this video about integer programming, and in the future know how to plant sugarcane optimally.